Hello, good evening, everyone. Can you hear me?
Yes, good evening, ma'am.
Good evening, ma'am.
Good evening, ma'am.
Good evening. So today is the first, not first, I think first session already happened on Monday. So in the first session, you had seen the theory of week one. I hope all of you have gone through the lectures by now, since it's Friday already. So what we will do today is we'll solve problems based on what we have learned in week one. Okay. So what will I do is I will present the question and I will give you some time and you can work on it first and then I will share with you the solutions. Okay. Kiran, you have any question? I see a hand raise.
Yes, ma'am. For the programming assignment, there is some concern like we don't know how to load the data sets.
Okay, so tomorrow one session will be conducted for programming assignment, so you can ask doubts over there. Okay.
Okay, tomorrow. But yeah.
Tomorrow is yes, programming assignment session. All right. So let's begin with the session. So the first question here is about the covariance matrix and the eigenvectors and eigenvalues, right? So you have the data set which lies in a D cross n dimension, all right? And we don't know what the data set is, but what is known to us is the covariance matrix C and their eigenvectors. So for this covariance matrix C, we have the eigenvectors given to us. So W1 and W2, they need not be like, it's not like a W1 has to be the first principal component and W2 has to be the second principal component. So it just that there is this data set that is given to us and that is there. And for that data set, we have this covariance matrix C. And for this covariance matrix C, we have these two eigenvectors, W1 and W2. Now, the very first question that is asked is, which eigenvector represent the first principal component for this data set? So that is the first question. And the second part is how much variance is explained by the data set. So I will just show you the question. I hope you remember the question part. So this is the information given to you, okay? So what you have to find out is which among the following is the first principal component. Is it W1 or is it W2? So I pasted the question in the chat in case you need it. So just work it out. I mean, give you a minute or two, and then we'll discuss what the answer should be. So anybody has any doubt in like what is the principal component? How do we find it? Anybody has any doubt in that? Okay, I will just move.
I don't know, ma'am, like how to.
Ma'am, can we use AX equal to lambda x?
You can do it, yeah. Okay, so for those who doesn't know from there, like how, like what is the principal component? So remember, like we have, like when we were going to week one, we saw that, okay, we have this data set, which is in D cross n dimension. And for this data set, we have a covariance matrix C. This covariance matrix C is what? Basically given by this x-axis transpose, right? This is, you take the matrix X, you take the matrix X transpose, find the product. Divided by n, and that is my covariance matrix C. So for this covariance matrix C, what you will do is you will find the eigenvalues and eigenvectors, right? So once you find the eigenvalues and the eigenvectors, you need to see which is corresponding to which is the largest eigenvalue basically, right? So whichever is the largest eigenvalue, that will give you, corresponding to that eigenvector will give you the first principal component. All right. So here you need to find basically the eigenvalue to figure out whether W1 is the first principal component or W2 is the first principal component. And also one note here that this W1 and W2 is of length 1. Okay, you don't need to compute its length. It's if you compute it, it will come out to be very close to 1. So you can just assume the length to be 1 for W1, W2. Once you are done, let me know in the chat or we'll see. Do we have any answers? Okay, I see one. Prakash has posted. So W2. Anyone else got W2 as the answer? Or ship? Okay. Okay, all right. So I see people posting W2 as the answer, and yeah, that will come out to be true. So let's go through it. See, what was given to us was just a covariance matrix and 2 eigenvectors. Now, what do we know? We know that my Ax is equal to lambda x, right? I mean, if you have a matrix A, I don't know. All right. So if you have any if you have any matrix A, right, and you have some eigenvector corresponding to its x, so it should satisfy this equation, right? Ax is equal to lambda x is the eigen equation that it should satisfy. Now, in this case, what is your A? My A is C, right? So, and what is your x? X should be my W, right? And lambda is my eigenvector, eigenvalue, and x is my W. Now, what you need to find is this lambda. We already are given the eigenvectors. What we need to find is lambda. So we can write this lambda to be Wi transpose Cwi. Are you able to understand why this is true?
Yes, ma'am. That sir has given in the lectures.
Okay,
Yes, derived it.
right? Yeah.
Mathematically, we are able to see, but I'm unable to visualize this.
Visualize this lambda.
Yes.
Okay, see, I mean, like, see, if something is in 2 dimension or 3 dimension, we can visualize it, but sometimes you might
Yes.
have to stick to
Yes,
maths to
I
understand this.
understand. The covariance matrix is a sort of a transformation.
Mhm.
then those for that transformation W1 and W2 are the are two eigenvectors. That I understand.
Mhm.
Then
So
this
lambda, what does lambda give it? It gives you the scaling, right?
okay, the scale, okay,
Yeah, it gives
yes,
you the scaling, right? But yeah, that, I mean, knowing that doesn't help it here in like solving it this problem, right? So
yes,
what we need to know is how do we we'll have to stick to the maths to find out this lambda. Now this lambda we can write it as Wi transpose Cwi, right? So there are two eigenvectors already given to us. One was lambda 1 and one was W1, another was W2. And W1 is given as your minus 0.894, 0.447, and W2 is given as 0.447, 0.894. All right. We work around it, and what we get is corresponding to the eigenvector W1, we have the eigenvalue to be 0. But corresponding to the eigenvector W2, we have the eigenvalue to be 5. So the largest eigenvalue corresponding to your covariance matrix C is 5, and this and this means that the second vector that is given to us, the second eigenvector that is given to us, this should be my first principal component. So this should be the answer. Okay.
So, ma'am, we can also just find the eigenvalue and find the eigenvector.
Can you repeat your question?
And then we can just directly find the eigenvalue and then find the eigenvector.
Yeah, that's exactly what we have done. No?
No, like I'm saying from the basic
Okay.
definition, we'll get like 1 minus lambda. Like,
Yeah, I get it. But okay. But the problem there is that I mean that's not a problem. But see, I mean you will find you have this covariance matrix given to you, and you will find the eigenvalues corresponding to this lambda 1, lambda 2, and corresponding to lambda 1, you will find W1, corresponding to lambda 2, you will find the W2, right? So again, you will have to find the principal component, right? But here, eigenvectors are already given to you. If you go through this method, it's not just you have to find the eigenvalues, you also need to find the eigenvectors. But here you are given the eigenvectors already, so we can use that and tell like, okay, this is the first principal component, right? In both ways.
Then the eigenvectors are just the like the null space, right? Null space of C minus lambda in this case. So that way, yeah.
Yeah,
Like
but
if I assume eigenvector should be some xy, then I'm getting like qx is equal to y. Then second option is I'm getting a condition based on that I can see.
yeah, you will get, I mean, you will get the same thing, basically. I mean, there are other ways also. I mean, there are many ways in which you can solve a problem, right? So both are okay. The way you have done it is also correct. That you have.
Yes, ma'am. Can you explain how does that formulation get from basic formula? AX is equals to lambda x, like lambda is equals to W I transpose C W I.
Which part? Okay, you are asking about this part.
Yes, can you-
This part, right?
yes.
Okay, see, your AX will, this is the equation. AX is equal, you know this eigen equation, right? AX is equal to lambda x.
Yes, ma'am.
Now here in place of A, you have C, and in place of X, you have W. You have lambda, you have W, right? Now you multiply both sides, left multiply both sides by W transpose. So we'll do W transpose CW. Same thing we'll have to do on the other side. So W transpose lambda W, right? Now lambda is just a scalar. So I can just pull it out and I can write this as lambda W transpose W, right? And now what we also know is that the length of W is just 1, is given to be 1. So I can write W transpose CW to be equal to lambda.
Okay. Got it. So here we are using immunity.
I hope this is clear.
Is always one, the length of the eigenvector?
What?
Is
Yes.
always one or?
No, it's not always one, but for this particular problem, the length is given to be one.
Where it is mentioned, man? It is.
Okay, it is. I verbally told that. It is not mentioned, but if it is given to you already, and if you try to compute this, no, like if you try to compute this length of W, so it will come out to be very close to.
Yeah, it is one coming.
Yeah, very close to 0.999 something. It comes out. So roughly, it's we assume that this is equal to one.
For this problem only, it is one.
Yeah.
Okay.
And like even in the lectures, we are sticking to the length of W to be one. So we'll stick to that equation. All right. So I hope the second problem is also clear from here, like how much variance is explained by the data set. So what do you need to do for that? You already find the eigenvalues. So what will be the variance? Any guesses? You have already found two eigenvalues. What is going to the variance? 5?
5.
Yes, 5 is the correct answer. So for the corresponding to the first principal component, the variance, the lambda was 5. And for the second principal component, the variation is coming out to be 0. So the total variance explained by this data set is 5 plus 0, which is 5.
How do we compute
How do we compute?
variance?
So variance is just your eigenvalues sum, right? I mean, you just find the eigenvalues and take its sum. That is your variance given by the data set.
And this 5 is explaining the spread of data, but I am not able to relate how 5 shows that variance.
I think this is covered. This was covered in the proof lecture. No, the proof was done. Did you go through that part?
I have gone through the lectures, the
Last lecture
total
or
lectures,
lecture.
but I can go through it again.
Yeah. So I think it's in this last lecture or second last lecture, if I'm not wrong. The proof has been given to you in case you are interested in like how this how this summation of the eigenvalue is giving you the variance.
Yes, ma'am, that I understand, but the unit of variance, I am unable to like understand why 5 is the variance. Okay, I understood that the scaling factor of of the largest eigenvalue, eigenvector, the largest eigenvalue value shows the variance, but 5 is
that shows the variance along the first principal component.
yes.
But now you have here two principal components, right?
Yes, that I understood. For the whole data set, the variance is 5, but this 5 has a unit or like is just a variance value?
It's just the variance value. It's not a unit. I mean, this is the variance you are getting.
Okay, ma'am.
Okay. All right. So second question is a simple question. Here you need to check which of the following are true with respect to principal component analysis, right? So the first option is all principal components are uncorrelated. It is primarily used for dimensionality reduction. Covariance matrix is always symmetric. The eigenvector with smallest positive eigenvalue is the first principal component. 2 and 3. Okay. 1, 2. Okay, see, I see a lot of different answers here. All right, let's go through it. So the first option was all the principal components are uncorrelated, right? So see, all these principal components, like we saw it with respect to for a small data set with two principal components we saw in the first example, right? And these principal components are all orthogonal to each other. So W1, if let's say you have a W1, W2, so on to WB, we saw that all of these are going to be orthogonal to each other, right? So means that not uh, they are not correlated to each other, or to say they are uncorrelated, right? So the first option has to be twice. See, some people did answer option A, but many of you missed the first option. So first option is true. The second one, I hope it's very straightforward. That is the main objective of doing the PCA. The third is the covariance matrix is always symmetric. So as it is mentioned here that the covariance matrix is given by XX transpose by N, right? And this matrix is symmetric. Okay, so this XX transpose divided by N. I mean, if you have solved some problems in the assignment, you had also observed the covariance matrix that you get. So the covariance of XY is equivalent to covariance of YX, and that is what we mean by symmetricity, right? So the third option is also right. The fourth option, again, it's I think it's very obvious from the statement itself that the eigenvector corresponding to the smallest positive eigenvalue is the first principal component, which is wrong because the eigenvector corresponding to the largest eigenvalue is the first principal component. So my first, second, and third option is right, and fourth one is wrong. Yes, it is always symmetric, Somdat. Yes. Okay. Let's see this question. You are given a center data set in R6 and the standard PC is applied on it. All the eigenvalues of all the eigenvalues of the covariance matrix for this center data set are given here, which is in decreasing order where lambda is greater than 1. So you have lambda 5, lambda 4, lambda 3, lambda 2, lambda 1. They are the eigenvalues given to you, and they're in decreasing order. So if the sum of the variances along the first principal component is exactly 88.88% of the total variance, then you need to find what is the value of lambda. I'll give you some time to think about this question. Maybe we'll discuss in a couple of minutes. No, center data doesn't mean variance is 0. No, it doesn't.
mean will be 0.
Yes.
Ma'am, is it lambda 2 or lambda square?
It is just lambda 1, lambda 2, lambda 3, lambda 4, lambda 4, lambda 4, lambda 5. It is not square, or it is not, it doesn't explicitly denotes a power. It's just the order. This is the order in which the eigenvalues are given to you, decreasing order. Any guesses for this question? How can we go? Okay, I already see one.
Sorry.
Okay. Manish has given the answer. Yeah, I'll just wait for maybe 1 more minute and then we can see. Okay. Let's see. Okay. It's a little tricky, but not very difficult. So, see, what is given in the question is these. I mean, you have a center, you have a data set in R6, and you have applied the PC on that, standard PC on that, and for this for this center data set, you have this covariance matrix and you have found out the eigenvalues for this covariance matrix. And what is given to us also is that the eigenvalues are lambda to the power 5, lambda to the power 4, and so on, right? And this lambda is given to be greater than 1. Now, if the sum of the variances along the first principal component is exactly 88.88% of the total variance, then what is the value of lambda? So you need to figure out the value of lambda, right? So, okay. So do you remember this part here? Like what one thing to note down is this one. So what is important to us is the first three principal component. So the first three principal component, and it is given to us that the variance it is exactly 88.88% of the total variance. So the first three principal component, the variance would be your lambda 5, lambda 4, lambda 3, right? And divided by the sum of all these eigenvalues, which is the total variance, right? So lambda to the power 5 plus lambda to the power 4 plus lambda to the power 3 divided by whole thing is basically your 0.8888, right? This is the information that is known to us. Okay. So once you know this information, all you need to figure out that what should my lambda be. Okay. So just for simplicity, like you see all these terms are like repeating, which is lambda to the power 5, lambda to the power 4, lambda to the power 3. And then this part, I can just take it as some other term. So this is my A, and let's say this is my B. So what we need to solve is this equation. Okay. So after solving this equation, what we get is this relation, which is A is equal to 7.99B. All right. So if A is 7.99B and I know what my A is and I know what my B is, then we can just solve these things. So I replace A with lambda to the power 5 plus lambda to the power 4 plus lambda to the power 3 and replace B by lambda square plus lambda plus 1. Okay. Now we can take this lambda to the power 3 common and we can just cancel these two terms, right? And what we get here is that lambda cube is 7.99. So approximately it will turn out to be 2. I mean, it's very close to 8, so roughly it is 2. So lambda value comes out to be roughly 2. So in the chat, I saw many people putting this as answer 2. Someone had put 2.66 as well. Manish, can you tell me how did you get 2.66?
Ma'am, I am simply do 7.99 under cube and write 2.66. No, not convert it to integer.
Will it come out to be 2.66? I know, right?
Yes, ma'am.
Okay, all right. If you have reached a lambda cube to the power 7.99, then it's okay.
Can you scroll up a little bit?
What did you say?
Can you scroll? Yeah, the initial part of the solution.
Yeah.
Thanks.
Ma'am, so here now, like I thought that these lambdas were different lambdas, right? For every round of this thing that we do, calculation that we do.
Okay.
This lambda to the power 5, power 4, like I didn't understand how that works.
Okay. See, the information that is given to us here for this question is that we have this covariance matrix C, and for this matrix C, I have the eigenvalues, right? And the eigenvalues given to us is 1, lambda, lambda square, lambda cube, lambda to the power 4, lambda to the power 5. Okay.
Okay, so is in this case it happens to be that the eigenvalues are like related to each other this way, is it?
Yeah, right. I mean, this is I mean, this won't happen usually, but this was more to test like whether you are able to do this part.
Okay. Okay.
Ma'am, what I tried doing was, if the first three principal component is giving 88.88%, then the other three components should give us 0.112 percent of the whole data set, right? Then the equation can be lambda square plus lambda plus 1 is equals to 0.112. Is that correct?
What did you write? Lambda square plus lambda
Plus 1
Hmm.
is equals to 0.112.
What about total variance? You need to do this, no?
Yeah, right.
You need to
Then the
divide.
equation will be similar only.
Yeah. Okay. All right.
Ma'am,
Yes, tell me.
I also had that confusion. I thought they are not powers.
Yeah, tell me, what is the confusion?
I mean, like in the MLF, they used to notate like this. Those I thought different lambdas.
Uh, oh, no, I didn't understand. In MLF, we used to denote it as different lambdas.
I mean, yeah, like lambda one, lambda two.
I mean, here also it's the same thing. It just see, you had the data set. It's in R6, right? And this covariance matrix will be in 6 cross 6, right? And you will get 6 eigenvalues. So you will have lambda 1, you will have lambda 2, you will have lambda 3, you will have lambda 4, you will have lambda 5, and you will have lambda 6. Okay. But now here what we are saying is that this my lambda 1 is given to be 1, lambda 2 is given to be lambda, or I think lambda square is given, right? No, lambda only. Lambda 3 is given to be lambda square. Lambda
Yeah,
4.
it's fine, ma'am. It's fine.
It's fine, no? Yeah. So,
Ma'am, just can you scroll a little bit up just once? The
yes,
initial part of the solution.
hold on. This is the, yeah. Here,
Yeah.
this page or is a little bit on it.
This is okay, ma'am. Just
Okay.
thanks, ma'am.
Yeah.
So also, ma'am, we can take lambda square plus lambda plus 1 common then.
Yes, you can take, but you make sure you divide it by the total variance. All right. So here is another question. There are 100 data points in R10, and lambda is the ith lattice eigenvalue of the Covariance matrix that you get. And these are the observations that are being made. So sum over lambda I from I varying from 1 to 10 is 200. Sum over lambda I from I varying from 1 to 4 is 140. And sum over lambda I for I varying from 1 to 6 is 180. If we wish to retain 90% of the information in the data set, then how many numbers do we need to store? I'll give you some time to think about this. Okay, I already got an answer, but please cross-check your answer, Som, whether it's not correct.
Ma'am, we will use a 6. 6 data set.
Okay. No, the question here is that if these are the information given, and if you want to retain 90% of information in the data set, then how many numbers do you need to store? Okay. Remember that you have the data points in R10. Just think about it a little bit.
Excuse me,
Yeah, tell me.
ma'am. Like this one, like summation I is equals to 1 to 10, lambda I is equals to 200 will be a one data set, correct? Or it
No,
will
no,
be 10.
it's not about one data set or two data set. There is just one data set. Okay. There is only one data set. This data set has 100 data points in it, and each of these belongs to R10. So it is more like that the data set that you have is X1, X2, so on till X100, right? And each of these Xi is in R10.
Got it.
Ma'am, 660. If I'm not wrong.
Yeah, okay. Let's see. 660, you said. Anyone else has any answers for this question?
I'm getting 106 actually.
How many numbers means how many eigenvectors?
No, how many numbers? How many numbers do you need to store?
Okay. The size, right?
So
size,
like,
right?
How many bytes we need to store? How many numbers means how many bytes we need to store? If we are talking about
okay. So yes, 660 is the right answer. I think earlier someone also had given this as the answer. Like I see a lot of answer 106, then 4 and 600. I mean, you're missing out on few things over there. I mean, you would have reached the correct, your approach is correct, but some few things you are missing of it over there. So we'll see how the answer is 660. So the very first thing, if you observe that we are interested in retaining 90% of the information in the data set, right? So, and so we have a total of 10 eigenvalues that we will get. So what we want is that the sum over lambda i's, where I is varying from 1 to we don't know how till how many, divided by the total variance should be 0.90 is what we want, right? So this whole thing is 200. So this is 200, right? So if we want this to be 90%, my lambda, my I should vary from 1 to 6, right? Because from like if you do lambda 1 plus lambda 2 so on to lambda 6, and then you need to do lambda 7 plus lambda 8 plus so on to lambda 10. This whole thing is just 200. The whole thing is 200, but this sixth component of this eigenvalue, still the sixth eigenvalues, it is already making it 180, right? So if you take I to be 6, you get just using these six eigenvalues, you are retaining the 90% information. Is it clear till here, like why it has to be till I varying from 1 to 6? Okay.
Yes, ma'am. Yeah.
So once this is okay, that we need to think about, we need to take only the first 6 eigenvalues. Then if the first 6 eigenvalues are important here, then we know that we need to store how many numbers is the question, right? So we need 6 principal components. Okay, so we need W1, W2, W1, W2, so on till W6. We need till here. So this will be, and each of these WIs will belong to R10, right? Okay, and how many are these? There are six of them. So there will be 6 times 10. So this will be 16. So you will need to have to store 60 numbers just for these principal components. Okay, but then it's not just the principal components that you need to store, right? You also need to store the projections. Let's say if this is my first principal component and if this is my data point, then I also need to store this projection along with W1, right? So I need to store all these X1 transpose W1, X2 transpose W2, right? So until X100 transpose W6. And these projections are just the numbers, right? So how many are these? These are 100. They are 100. And there are total of 100, the total of 6 principal components, right? So 100 into 6. So we'll do 100 into 6. 600 from here and 60 coming from the principal components. So total of 660 numbers is what you need to store. Yes. Basically. Okay, I didn't see what was in the chat.
Like basically, it's that total number of you
have to figure out how many numbers do you need to store if you want to retain 90% of the information.
Yes.
Okay. I think just this should be 1, right? And then you do it for 6 of them, so 600. So is this clear?
Yes.
Okay. All right. So this is a very simple question. So you have this data set, and in this data set you only have 6 points, and which is an R2. So this is R2, and what we're saying is that there are 6 points. So somewhere there are 6 points. Let's say 1, 2, 3, 4, 5, 6. Let's say these are the 6 points that we have. So what is given to us is there are 4 lines. So this one line, second line, third line, and 4th line. And these are the 4 lines, and on which the projections has been done. So all the 6 points that you see here, so they are being projected on these 4 lines. Okay. So if these points are projected on these lines, you see the projections as the tiny black dot on each of these lines. So since there are total of 6 points, so you will see 6 points. So 1, 2, 3, 4, 5, 6, right? Look at the red line. So 1, 2, 3, 4, 5, 6. So these are just the projections of these data points onto these lines. Now, if that is the case, then the question is, which among the following lines could possibly be the first principal component?
The yellow line with the maximum variance.
Yes, the yellow line with the maximum variance, correct. I hope this is clear to everyone.
Yes.
Yes, ma'am. This is simple.
Ma'am, are these PYQs?
No, they are not PYQs. Okay, here is another question. So you are given these data points x1, x2, x3, which is in R2. So x1 is 2, comma 2, x2 is 1, comma 2, x3 is 2, comma 1. So if you write it in the matrix main vector form, it is this, x2 is 1, 2, and this is 2, 1. Okay. So the first question is, what is the mean of this given data set? And the second is, what is the covariance matrix? So first, let's just do the mean of the data set. I will wait for some time, and then if you calculate, just put in the chat.
5 by 3, 5 by 3.
Yes,
Okay. Yeah, I hope all of you got it. How to do it? So it's a very simple problem. Like you are given three vectors, and you just need to find the mean. So what we will do? We take the first component of these vectors, and we find the mean of that. So we'll do 2 plus 1 plus 2, which is 5 divided by 3. Then similarly, we'll take the second component of these vectors, and we'll do divided by 3. So 2 plus 1 again. So 5 by 3, 5 by 3 is the mean of this data set. Now coming to the second part, what is going to be the covariance matrix C? So to find the covariance matrix C, what do you need to do? You need to do 1 by n xx transpose. Okay. And x is going to be the what? X is going to be your centered matrix, center data set, right? So first, you have already found the mean. Find the center data set and then compute the covariance matrix. The question is to find the covariance matrix C, so it cannot be 0. Okay? So please work it out. wherever you have put three components to it, like you need to have a 2 x 2 dimension matrix and not a 2 x 3 dimension to check your calculations.
Actually, ma'am, I have just provided the center data set, not the covariance matrix.
Oh, okay, all right. Okay. All right. So I see many answers in the chat. So okay. To find the covariance matrix, what is the first thing that we need to do? We have this. We need to first find the centered matrix X, right? And then we do XX transpose divided by N. So that is the goal. Now, the mean we had calculated, and that was 5 by 3, 5 by 3. So if we have to find uh, the centered data, right? So what we need to do, we need to do xi minus x bar, x1, which is in this case x1 minus x bar, x2 minus x bar, and x3 minus x bar. So my x1 was 2 comma 2 and x bar was 5 by 3, 5 by 3. So we got this to be 1 by 3 and 1 by 3, right? Similarly, x2 minus x bar we do, x3 minus x bar we do. So what we got is that the centered data, right? So my x currently is 1 by 3, 1 by 3, right? And the second component is minus 2 by 3, 1 by 3. The third is 1 by 3 minus 2 by 3. All right. So this is my x. Now, if you take the transpose of this, you are going to get a 3 x 2 matrix, right? And you just divide, I mean, you calculate after that XX transpose. And once you do that, you just divide it by n, and that is going to be your the final matrix. I mean, the final covariance matrix C. So let me see in the chat. I have not solved it in this part. So by so all of you who have gotten 2 by 3 minus 1 by 3 minus 1 by 3 2 by 3, there you need to see the covariance matrix is 1 by n xx transpose, right? So you need to divide it by 3 there because you have 3 data point. Then the answer that you should get, I will just write the final answer that you should get here. um, the final answer that you should get, which is 1 by n xx transpose, is 2 by 9 minus 1 by 9 minus 1 by 9 and 2 by 9.
Yes, ma, I just realized that I missed it and I have re-uploaded
Not
recently.
problem. Yeah. So whoever got this as the answer, it's correct. Even who have not divided by n, it's kind of correct, but you need to divide it by n to get the correct answer.
Can I see the covariance matrix once?
Yes. Is this what you wanted?
Yes, ma'am. Thank you.
So you can, if you want, you can also like, I mean, we got this covariance matrix. If you want, you can proceed with finding the eigenvalues, finding the eigenvectors, and the principal, finding out the principal components. But we are not going to do it here. But if you, just for the practice, you can do it. Okay. So once you have the covariance matrix, what is going to be the first principal component, what is going to be the second principal component is something that you can find out. Any doubt in this question? I hope it was okay. All right. Okay, let's move to the next question. So this is also a little tricky. Let's see. In this question, you have 6 data points given to you. X1, X2, X3, X4, X5, Xx. The length of the projections of these 6 data points are on to my first principal component W1, and these X1, X2, X3, X4, X5, Xx are my data points. So somewhere they are, okay. So these 6 data points I have, and the length of the projections onto W1 are given to you. So let's say if this is my data point 1, this is X1. The length of the projection is given to me as 8. All right. Then if let's say this is my X2, the length of the projection onto these data point is given to be 7, and so on. So these are the length of the projections. Now, given this information to you, like what you know is that for these 6 data point, for X1, X2, X3, X4, X5, X6, we don't know what these data points are. We don't know what are the what is the first principal component. All we know is that for the first data point, if we take its projection onto the first principal component, it's going to give me 8. For this, the length is 7. For this, the length is 3. For this, the length is 5. For this, the length is 2. For this, the length is 4. So you need to find out what is the variance along the first principal component. I will give you some time. This might take a little bit of thinking here.
Ma'am, variance can be represented in terms of squared errors, some squared errors.
Yeah, yeah. You take your time and see what answer you reach. We'll discuss this. All right. I see many people have answered 5.37. So, can you tell me how did you do this problem?
Like first finding the mean x bar, then after that xi minus x bar whole square, and after finding the sum of the
What is
variance.
xi minus x bar here? I mean, we don't know xi, right? How do you find xi minus x bar?
Like here it is given x1, so it will be xi.
No, those xis, this 8 is the projection of x1 onto w1. It is written in the question, you know. So x1 is the project, sorry, this 8 is the projection of length of projection of x1 onto w1. This 7 is the length of projection of x2 onto w1, and so on. Okay. So the projections are given to you. The length of the projections are given to you. What we need to find is the variance along the first principal component. So if you remember, the variance will be given by 1 upon n sum over xi transpose w1 squared, where I is varying from 1 to n. There is a variance along the first principal component. Do you remember this?
Yes, ma'am.
Yeah. So now, if this is the variance along the first principal component, and these are already given to us, right? So xi transpose w1, its length is given to us as 8. Xi transpose x2 transpose w1 is 7. X3 transpose w1 is 3. So on. So they are given to us already. So what we need to do is just we need to take this squares and divided by 6, and that should give us the answer here, right? So we'll do 1 upon 6 sum over xi transpose wi square, I varying from 1 to 6. And if we solve for this, I mean, if you take the square, these are the squares that you get, and the final answer will come out to be 27.83. So someone had given Manish, your answer was correct. Someone got Shanmugan, you got 29 as the answer, and it's very close. Can you tell me, like, how did you get this answer, 29?
Madam, I saw with the geometrically, I understood that the projected portion is the variance.
Okay,
So
okay.
that's why I added up all the values to get the total variance. So I got confused a little bit. Now I am clear.
Okay, okay, all right.
Thank you.
I hope this is clear to everyone. This what had to be done in this question.
Yes, ma'am. Actually, I thought it is given that xi, so that's why
No,
xi.
those were not exercise. It was like when I wrote this x1, 8, x2, 6, they were not data points. When I was speaking, I told that these are the length of the projections. So just read the questions, okay, before you attempt solving.
Yes, ma'am, got it.
Okay, let's move to the next question. So here, the question again, you have 6 data points. And now in this case, what is asked is the length of the projections of these 6 data points onto W2. So it means the second principal component that we're talking about are these 1, 2, 1, 3, 2K. W2 is the second principal component. The average here due to projection onto W1 is 28 by 6. Okay, and W1 is the first principal component. So if the average error due to projection onto W1, so if you see here, this is nothing but my W1. So the average error due to this projection is coming out to be 28 by 6. Again, this is W1 is not 28 by 6. The average error due to projection onto W1 is 28 by 6. So if this is the average error and what you need to find out is what should be my k. So it's kind of an extension of the question that we solved in previous one. This is like now projecting it on W2 is what you need to check. I'll give you some time for this question.
Three will be the answer, ma'am.
We will check whether. Let's wait. Okay, so all of you are getting the answer as 3, which is again correct. So let's go to the solution. So here, what was asked? I mean, you had this 6 data points: x1, x2, x3, x4, x5, xx in R2, and uh, the length of the projection of these 6 data points onto W is what we're talking about. So now this is my W, right? This is going to be my W. Now what we have to do is length of these. Now the length of the projection of these 6 data points. So for x1, the length of the projection is given to be 1. For x2, the length of projection is given to be 2, and so on. So what is not known to us is what should k be. So corresponding to data point x6, what is the length k? What is the projection of the data point x6 onto w2? So that is given to be k, but we don't know what this k is. But what additional information is given to us is the average error due to projection onto W1 is 28/6. So this is what we will use to solve this question. Okay, so if the average error due to projection on W1 is 28/6, it means what can we say from here? We can say that 1 upon n, which is 1 upon 6, sum over xi minus xi transpose w. This is going to be 28/6. We can say that this is the average error, right? So if this is known and this is also known to us, then all it needs to do is to just solve for this, right? So if we solve for this part, so now, yeah. So this is known to us. This is known to us, and that is 1, 2, 1, 3, 2, k. So we just solve for this equation and we get k to be equal to 3. Anybody has any doubt in this? Okay.
Geometrically, can we say if these are orthogonal, then the errors will be similar, is it?
The errors will be similar.
Will be
What do you
same.
mean by similar here?
Ma'am, here W1 and W2 are orthogonal, that is understood. So how this result is making sense, I understood mathematically, but if we see geometrically, these are orthogonal. So the sum squared error of both these vectors of the projection should be equal.
Yeah, I mean the length of the projection. So what is your error vector first of all? So if this is my error vector, right? If this is my data
Yes.
point, this is my error vector. Okay.
Yes.
Now what are we saying? The length of these error vector are the length of the projections onto W2.
Yes.
So if you project this onto this my W2, you project this onto this. This is my length of the projection onto W2, right? If you look at this, so maybe it's very tiny. Maybe let's just do this. So this is going to be the length. So these are the lengths that you get, and these lengths are given to you, right? I mean, you'll get 6 such vectors here, right?
Yes.
This is how it will look like, and these are nothing but my xi minus. So if I take for x1 minus x1 transpose w1 times w1, right? x2 minus x2 transpose w1 of w1. So these are the lengths. Right?
Ma'am, generally can we say if two vectors or two lines are orthogonal, can we say the for a reference point, the error vectors for both these vectors should for both these lines should be equal?
the error vector for both these lines.
Uh-huh.
Uh, what
In
what
reference to a given data set.
what line are you talking about?
W1 and W2 only. These are orthogonal lines.
Hmm.
And if the projections, let's say projections slash error vectors
Hmm.
should be equal.
Yes, yes, yes,
Okay.
yes.
In reference to a given data set only.
Hmm. Um, yeah. I mean, for any data set, this will hold, right?
Okay.
I think this also we have seen in the lecture, this part. Any other doubt in this question? All right. Let's move to the next one. So this is a simple question. Uh, so I mean, there can be various answers possible for this. So let's see. So there are 4 data points, which is an R2, and it lies on a line passing through the origin. So you have x1, x2, x3, x4. x1 is -2, -6, x2 is -1, -3, and so on. Now, if these lines if these points are on a line passing to the origin, you need to find a representative for this data set such that W is equal to norm of W is equal to 1. Again, various answers are possible, so please feel free to give your answer in the chat. Anyone else who wants to give your answer? I see 3 already. You need to find, very simple question. You need to find, you're given this data set. You need to find representative W for this data set. Representative as in like, what is that vector that can represent all of these data points that is given to you?
It should be the projection, right?
Okay,
one by root 10, comma 1, 3 by 2.
Yeah, so all the answers in the chat is right. So many different answers are possible here. So yeah, 1 by root 10, 3 by root 10 is again correct, 2 by root 40, 6 by root 40 is again correct. So many different answers are possible. So I hope you got how to do this. I'll just talk about this. So if you look at this, these data points, they are basically following this equation, which is y is equal to 3x, right? So for every y you see, this is nothing but 3 times of x, right? This is 3 times of x, this is 3 times of x, 3 times of x. So we need to have, we can have any point which lie on this line, right? And there can be many such points possible. But what we need to do is, once we give a point, let's say I give the point 1, comma 3. So if I give this point, I need to make sure that this length is 1. So I'll just divide this by its length. And what is the length of this vector? It is root 10. So 1 by root 10 and 3 by root 10 is one of the possible answers. Okay. All right. Anybody has any doubt in this? I hope it's clear. Okay. So this was the last question. Any doubt you have? Anything that we discussed? Any issue? Any doubt? Last question you want to know. So last question was this. Okay. Last question was, if you are given a data set that has 4 points, which is an R2, and these 4 points are on a line that passes through the origin. So if you look at these data points, you can easily see that this is lying on the line y is equal to 3x. So you need to find a representative for this data set. Okay. That's all. Karthik, will the recording be available? So this is already being live streamed. And the link is already put on the calendar, so you can check over there. All right then. There is nothing we can close then.
Ma'am.
Yes, Karan. Tell me.
Ma'am, when I was doing MLF, your lecture was very helpful for me for understanding PCA, those equations and all. Like I searched in YouTube, but only theory got clarified. I was like frustrated by those lectures. That time your session was very helpful. I
In
think it
MLF,
was. Hmm?
in MLF you're talking about?
Yeah, for PCA, those derivations.
Okay. And thank you for that. Yeah.
Those notations are a bit different, no? In
Notations
YouTube,
are different. What we had done in MLF and what we have done in MLT. The notations that are used are different, and the way it has been done in both these courses are a little different.
oh, okay. Thank you.
Yeah. I think here I
Um,
would say in MLT it's much more simpler what we have seen in MLF, I guess.
Ma'am, I have a doubt in a graded assignment of week 1.
Wherever graded assignment we can't discuss.
Okay. Ma'am, the same question is also in the practice assignment. Can you go
Okay.
through that?
Okay, tell me the question number.
Ma'am, is it actually related to the graph, but I didn't remember the number. So if you show me in the screen, I will tell
You
you.
can tell me the number, no? You can tell me the number.
Okay. Can you wait for 2 minutes? I will tell you.
Okay.
Ma'am, my doubt in programming assignment.
Okay, so for programming assignment, there is a separate session conducted tomorrow at 6 o'clock. So you can attend that if you have any doubt in programming part.
Okay, ma'am.
Okay. No, there are no more questions. So, if you have anything else, we can we'll discuss. Otherwise, you can drop off. In calendar, it's not showing any session. It should be there. It is there. You refresh it and check. It is there at 6 o'clock. Yeah, okay. Thank you, everyone. You can drop off.
Just 1 second, ma'am.
Yeah, I am waiting. The PDF will be uploaded on the portal.
Yes, ma'am. Practice assignment 1, question number 13.
Question number 13. Assignment 1 question. And you're saying this is similar to which question in GA?
With the last one of the graded assignment.
Last one of graded assignment. Wait, hold on.
Means concepts are always little bit similar. If I'm able to do the practice assignment question, then I should do it in the graded assignment.
Yeah, that's there. All is there. Is it possible for you to share your screen?
Actually, ma'am, I am on my mobile phone, not on my laptop.
Okay, let me share them. Sure. Yeah, this is the question, right?
Yes, ma'am. Yes, ma'am.
Just to be here. Yeah, tell me. What is the doubt in this?
Ma'am, I am not able to attend this question. Not able to do it, actually. Means lagging in the concept.
Okay. What does it say here? I mean, you are given an image. So there is this vector W. Sorry, I mean, this figure is just too big. It doesn't fit here. So this W is the vector, and L is the line, I think, perpendicular to W. And there are two regions given to you, R1 and R2. Okay.
Yes, ma'am.
So if X is an arbitrary vector in the plane, select all the correct statement. So, okay, do you know about hyperplane?
No, ma'am.
You know,
But my doubt is just like that. If I am talking about the vector W, which is in a region 1, in this
then
region,
if
ma'am,
we satisfy, then in region 1, all the points will hold that region 1 will have sort of all points such that your W transpose X will be positive.
but ma'am, actually, W transpose X means a dot product. In the second quadrant, the cost value is always negative because from in second quadrant, the cost value is 0 negative. And we do the dot product of W and X, then it will become WX cos. Then it will comes negative now. How it is showing the answer is positive.
No, it's see, your W is in this second quadrant. You see,
Yes,
W
ma'am.
is in
Second
second
quadrant.
quadrant, and this W transpose X, if you do, And where does x lie? So x is any arbitrary vector in the plane. So x can be anywhere. Okay. So
Okay.
if I'm talking about any point in region 1, you take any point.
Yes, ma'am.
Okay. So so if you take any point in region 1, it will satisfy uh, so it will satisfy the set of all x such that W transpose x is positive. You're talking about
Actually,
the cos theta, right?
ma'am, actually, what I want to know, ma'am, the
Yeah,
W transpose X means the dot product of W and X.
correct.
When we expand it, we get a W X
Mm.
cos, and the angle in second quadrant, but in the second quadrant, the cos
So dot
will
product
be
of W
negative from
and x
0
is
to
what? Dot product of W and x is what?
ma'am, you are not audible.
Your voice is speaking for me. No, I'm saying, how do you write the dot product? Hello? Can you hear me? Am I audible?
Yes, no.
Okay. Okay, I think Weber is here.
Yes, ma'am, I am here.
Okay, you were not audible to me. Were you saying something?
Yes, ma'am, I am saying that uh,
Okay, you tell me what is the dot product of W and X?
on W and X is
If
a WX
norm of
cos.
W, norm of X cos theta, right?
Yes, ma'am, yes.
And what is theta here? Theta is the angle between W and X, right?
Yes, ma'am.
Now, if you take any X in region R, any X, okay, what
Yes,
is
ma'am,
its
yes, ma'am.
angle going to be with respect to W? It is going to be lesser than 90 degree, right? So the cos theta value will be positive, right? You get my point?
Yes. Yes, ma'am, it will be lesser than 90.
Yeah. So W transpose X has to be greater than 0, right? In any point lying in this region R1. Is it clear?
But, ma'am,
Sorry, your voice broke again. Is it clear what I just said? See, you have to take any X that you take, right? Let's say this is X. Now, what is the angle between these two? This is just going to be theta, right? And cos theta is going to be lesser than 90 degree. So that is going to be greater than 1 and not lesser than 1. So
yes,
W
ma'am, yes,
trans,
ma'am.
you got it?
Done. Yes,
Yeah.
ma'am, done. You
Okay.
are saying that the angle between W and X will be
Mhm.
acute between 0 and
Uh,
90, and
yeah.
the angle between 0 and 90 is always positive for cos.
Yes.
Thank you, ma'am.
Yeah. Okay.
That's it, ma'am. Thank you.
Okay. All right. Thank you, everyone. We'll meet again on Monday.